Hi everyone! These notes are an introduction to trigonometry, or for most of you probably a review of some basic trigonometry you saw in geometry class. Trig is really the study of certain ratios that exist in a right triangle. It's important to realize that these three ratios we talk about only apply to right triangles. Of course, once we've established them in right triangles, we see how they're useful later on in other types of triangles. But keep in mind that every triangle we draw for today is going to be a right triangle. The three trig ratios are sine, cosine, and tangent. And you can see the way that we spell those three words right there. Take a look at the triangle that's drawn to the right. Notice I've marked this angle and I've used a Greek letter known as theta to describe that angle. That's a very common letter. It's a very common Greek letter that we use to define an angle, and it's pronounced theta. Notice once I've defined an angle, certain sides now of the triangle now have specific names. I can look at the side that is opposite that angle theta. So this side is the opposite side. Of course, if I turn the triangle or I start talking about this angle, suddenly a different side would be the opposite side. But notice for this slide, we're always going to be talking about this angle right here for now. Notice the side that's right next to this angle is this adjacent side. So we name that the adjacent side. You might be saying to yourself, wait a minute, this side is also adjacent or next to this angle theta. But because this side is opposite the right angle, we have a more special name for that side. We call it the hypotenuse. So once you've denoted an angle, you can then label the sides of your right triangle, the opposite side, the adjacent side, and the hypotenuse. And depending on where your angle is in the triangle, you'll have to figure out where those names go. Let's go back to our definitions. Sine of an angle, by definition, the sine of an angle we abbreviate SIN, and I'm going to talk about sine of our angle theta, is equal to the opposite side over the hypotenuse. I'm just using these abbreviations so I don't have to write out the whole word, but you know that op means opposite and hyp means hypotenuse. Notice how we abbreviated that word sine, S-I-N. We would still say sine. I know it looks like the word sin, but it's not. It really does mean sine. Notice I had to put that angle theta next to it. I don't know if I was talking about sine of this angle, sine of 37 degrees, or sine of this angle over here. So we have to always put whatever angle we're talking about next to that trig function. Cosine we would abbreviate just as you want, COS. The cosine of our angle theta is going to be defined as the side that's adjacent to that angle over the hypotenuse. The tangent of an angle looks like tan theta, and that's going to be defined as the opposite side over the adjacent side. These definitions don't change. The cosine of an angle is always the adjacent side over the hypotenuse, but it's the measures of these sides and the placement of the angle that might change. So we have to be very careful about these ratios. Do you know a nice way of remembering how these ratios exist? Well, if you don't, there's a cool word that helps us. It's not really a word, I guess, but it's more of a mnemonic device. The sine of an angle is the opposite side over the hypotenuse, SOH. The cosine of an angle is equal to the adjacent side over the hypotenuse, CAH. The tangent of an angle is equal to the opposite side over the adjacent side, TOA. SOHCAHTOA is a made-up word that helps us remember the ratios. So you'll hear me say that, and I'm pretty sure I actually have it written on the next slide for our example. Take a look at that. I have SOHCAHTOA written in the top right-hand corner of our slide so we don't forget our order of our ratios. And I would like to find out in this picture, what is sine of theta? Well, I look at my ratio, I know sine is opposite over hypotenuse. So if I'm talking about this angle theta here, the opposite side is x. the hypotenuse is y. So sine of this angle theta is x over y. Cosine of angle theta, look at my trig weird word, cosine is adjacent over hypotenuse. The side adjacent to angle theta, in this example, is w. Our hypotenuse is still y. Notice the denominator for sine and cosine is the same, because the denominator is the hypotenuse in each of them. The tangent of angle theta is equal to x over w, opposite side over adjacent side. If you have trouble figuring out which side is which, you can kind of draw an arrow from your angle across the triangle, and whichever side you're pointing at, that's the opposite side. The side that's not the hypotenuse then is the adjacent side. And of course, the longest side in your right triangle is the hypotenuse. If you're wondering why these ratios are the way they are, then we might need to do a little bit of history of trigonometry to learn. But as for right now, we can just accept them as definitions of three functions. Let's do another couple of examples. I'd like sine, cosine, and tangent of angle theta. So let me kind of set up what I'm looking for right here. Sine of theta, cosine of theta, and tangent of theta. Well, notice where theta is in this case. It's up here now. It's not on that bottom left angle. Of course, the triangle won't always be oriented in the same way, and the angle is not always in the same position. Sine, let me write SOHCAHTOA so I remember what's what. Sine is opposite over hypotenuse, and I can see that here's the opposite side, 3. The hypotenuse is 5. Not so bad, I actually have numbers in this example. Cosine of theta is adjacent over hypotenuse, but we're missing the adjacent side. What is that side equal to? Well, here's a great example of how we have to use our previous knowledge of right triangles to find that missing side. It's a right triangle, and we know 2 out of the 3 sides, so we can use the Pythagorean theorem to find that missing side. 3 squared plus whatever that side is squared equals 5 squared. That's Pythagorean theorem, and we had to know to do that first to find that missing side. When we solve this, we get that x squared equals 25 minus 9, which is 16. X equals 4. You might have known that already from the Pythagorean triple, 3, 4, 5, my favorite one. Now that I found that missing side, we can go back and fill in our missing trig values. Cosine is adjacent over hypotenuse, 4/5, and tangent of angle theta is opposite over adjacent. Notice I always wanted to look where the sides were in relation to the angle in question. I couldn't always assume that a specific side is always the opposite side, because if I flip my triangle around, it's not the case anymore. Let's do one last example. I'm given very minimal information here, but I'd still like to know sine, cosine, and tangent of one of the missing angles in this triangle. First, let's see if we can fill in what we know. It's isosceles because of the markings, so that must also be 6. If the 2 missing angles are the same, and they have to add to 90, then we know that we actually have a 45, 45, 90 triangle. Any isosceles right triangle is a 45, 45, 90 triangle. I could use Pythagorean theorem to solve for the hypotenuse, or I could remember my special right triangle relationships. I know that that hypotenuse is 6√2. What I would like to know now is sine, cosine, and tangent of 45 degrees. Notice I'm naming it 45 degrees instead of just angle theta, because in this example I actually know the angle measure. So there's no point in just saying sine of theta when I know that in this case it's actually 45 degrees. Sine of 45 degrees, well, let's see, opposite over hypotenuse, 6/6√2. I could reduce that fraction, cancel out those 6's, and call that 1/√2 if you want. Cosine of 45, well, cosine is adjacent over hypotenuse, so adjacent over hypotenuse. Also 1/√2 once we reduce. Why is it the same as sine of 45 degrees? Well, in this case, the opposite side which is 6, is the same as the adjacent side because it was an isosceles triangle. So here's an example of when sine and cosine actually have the same value when our angle's 45 degrees. Lastly, tangent of 45, opposite over adjacent, 6 over 6, which is just 1. So what's really cool about these special right triangles is that I actually know sine, cosine, and tangent of 45 degrees. I actually know the values when we're given a specific angle. If I, instead of 6, 6, 6 root 2, maybe it was 10, 10, 10 root 2, would these ratios change? No. We'd still be able to reduce, and we'd still get 1 over root 2, 1 over root 2, and 1. Think about what other sine, cosine, and tangent values you might know. Maybe if we had like a 30, 60, 90 triangle, we have some special relationships there as well. But I'm hoping that this video was a good refresher on how to use SOHCAHTOA and also how to find sine, cosine, and tangent of some specific angle measures. Good luck!